All right, so thanks very much. In the time we've got, there was no way that we could actually, cover every issue related to nuclear things that might come up. So there's plenty of stuff that we can cover in Q&A. For example, in this little segment of 3 sets of sort of technical background, we're not covering ballistic missiles, cruise missiles, bombers, all the stuff that President Putin was talking about in his speech, but we can cover that in the Q&A. We also don't have a lot of time devoted to nuclear power, but again, we can talk about that in Q&A. So just a few thoughts on nuclear weapons, how they work, what their effects are, just to give us a grounding in what we're talking about here. So this is Nagasaki. After the nuclear bomb was dropped. This is taken in September of 1945. And you can see basically the incredible transformation was a single bomb can obliterate the heart of an entire city. And the amount of material required is small. So this ball is a glass ball that is the same size as the plutonium that was in the bomb that did that to Nagasaki. And you can see that person is holding it in their hand. So I'll talk more in a minute about the different kinds of nuclear weapons, but if you want to do the simplest kind with highly enriched uranium, or HEU, it takes about 50 to 60 kilograms of that material, which is, it's very dense stuff, so it fits in 2-liter bottles, basically. And then for the Nagasaki bomb, 6 kilograms of plutonium. Or for a similar design, it would take about 3 times that amount of highly enriched uranium because it's not quite as reactive in a nuclear sense as plutonium is. So all this comes from the fact that each atom that splits releases a ridiculously huge, on an atomic scale, amount of energy. It's about 10 million times more than when something participates in a chemical reaction. And the reason for that is that an atom is a collection of protons and neutrons and so on, and the electrons are in this haze around the atom that is very loosely bound, and they're what's taking part in the chemical reactions. So if this is my nucleus, some of my electrons are like over here, if I'm bringing the nucleus to scale. Whereas when you're actually going right into the nucleus and dividing it, that's much more tightly bound, and so there's much more energy, about 10 million times to 100 million times more energy per atom taking part in the reaction. And that's why you can get, out of a small little ball, enough energy to destroy a city. It's also why you can get a lot of power for civilian power out of a relatively modest amount of fuel. So in nuclear power, the reason it's expensive is it's expensive to build the plant. Once you build the plant, the fuel is practically free. You need very little fuel. So one type of nuclear weapon is what's called a gun-type bomb. This is the simplest. It is literally slamming 2 pieces of highly enriched uranium together at high speed. The bomb that obliterated the city of Hiroshima basically was a cannon that fired 1 chunk of highly enriched uranium at another piece of highly enriched uranium. This is quite inefficient. Only about 1% of the uranium in the Hiroshima bomb actually split. And you can only really do that with highly enriched uranium. Because plutonium naturally has the atoms of plutonium fall apart by themselves all the time. And so there are neutrons flying around from plutonium. And if you start moving those 2 pieces together, as soon as it gets close enough that it's what's called a critical mass so that the chain reaction can get going, it will get going, and before it's compressed enough to really give you a decent yield. So if I had a gun-type bomb with plutonium, I could kill everybody in this room, but I wouldn't destroy Cambridge, Massachusetts. So with plutonium, or if you want to be more efficient with your highly enriched uranium, you have to go for an implosion-type bomb. And what that means is that you're taking the nuclear material and you're crushing it to a greater density. the reason that helps is when the atom splits, it releases a couple of neutrons. They go on and split other atoms. So, and you need to split a huge number of atoms in order to get a decent amount of energy, because atoms are teeny and the amount of energy from each one is teeny tiny. And what happens is the material heats up and starts to expand back out. And if the atoms aren't close together, then when they release the neutrons go flying off into the surrounding countryside without hitting another atom. If you can make it more dense by using explosives to crush it down, then the atoms are really close together, and the probability of a neutron released from an atom hitting another atom and splitting another atom and so on before they go off into the surrounding countryside gets much better. So you take the same amount of material, crush it down, and all of a sudden it's a critical mass and you set off your nuclear bomb. This is not the Trinity test bomb. It was a sort of test, a sort of cold test before then in an earlier design. But you can see they have these lenses of explosives. And what those do is they focus the explosion in a sort of circular shock wave down on this ball and crush the ball. Now this ball is way, way bigger than the actual plutonium. The actual plutonium is like in there. This has got all sorts of other stuff around the plutonium. So this is definitely more complicated to do. It would be more difficult for terrorists to achieve a implosion bomb, but still plausible, and doesn't have to be as complicated as the Nagasaki bomb was. And that's about as much as I'm allowed to say, but it really doesn't have to be as complicated, unfortunately. I remember thinking of one simpler approach at one point and thinking, oh, gee, if that works, that's probably classified. And talking to a nuclear weapon designer, said, yeah, it works, and yeah, that's really classified. So, but modern nuclear weapons are mostly thermonuclear weapons, meaning they're not just splitting atoms, they're also putting atoms together, taking tiny little light atoms and fusing them together. So splitting a big unwieldy atom like uranium or plutonium releases energy, and putting tiny little atoms like hydrogen together also releases energy. So what happens in a modern thermonuclear weapon is you have a normal fission weapon, more or less, which is called the pit or the primary, and you take the energy from that and focus it on what's called the secondary, which has fusion fuel in it. And that takes that fusion fuel to unbelievable temperatures and pressures, comparable to the center of the sun. That then causes the fusion reaction to take place. But the fusion reaction also releases a whole bunch of neutrons. And so the designers were, well, why should I waste those neutrons? And so you put in a lot of uranium, and then you get more fission as well. So in the end, for a lot of typical thermonuclear weapons, you might have half of the energy coming from fission and half coming from fusion, more or less. By the way, stop me if you have questions.
So what defines thermonuclear as opposed to the other kinds of nuclear?
So the normal nuclear is fission, so I'm splitting a heavy atom, and thermonuclear is fusion. I'm putting together the light atoms. But as you can see, it really is fission plus fusion at the same time. We've never figured out how to set off a fusion reaction without the energy from a fission bomb. That's been sort of the holy grail of nuclear designers, since way back, but nobody's ever achieved it. So, you can't make a nuclear bomb with just anything. There's basically two main materials that nuclear bombs in the world today are made of, that is the fission parts of them. One is highly enriched uranium, and the other is plutonium. Now, and Kate will describe how these materials are made, but the uranium you dig up out of the ground is useless for nuclear weapons, to first approximation. The kind that splits is uranium-235, and that's only 0.7% of the uranium you dig up out of the ground. More than 99% of it is uranium-238, which is basically useless. But what you can do with uranium-238 is put it into a reactor where there are a lot of neutrons flopping around, and the neutrons hit the uranium-238 atoms, and instead of splitting those atoms, it absorbs those neutrons, and it decays a little bit and then turns into plutonium. There are a few other isotopes you can conceivably use to make nuclear weapons, but nobody does.
And plutonium exists in nature or only through?
Neither of these exist in nature in any significant quantities. There was an amazing event a couple of billion years ago. So the half-life of uranium-235 is 3/4 billion years. So 2 billion years ago, there was a good bit more uranium-235 around than there is today. And in a place in Africa, there was a particularly rich uranium deposit, and water got in there, which slows down the neutrons and makes it a bit easier for them to split atoms. And natural nuclear reactors started going and produced tons of plutonium over the time that it was going. But plutonium has a half-life of only 24,000 years only. So, the plutonium made 2 billion years ago is pretty much gone at this point. So you can still detect atoms there, but that's better.
Wow.
So what are the hard parts of making nuclear bombs? Number one, and I would say number 1, 2, 3, and 4 is making the nuclear material. That was about 90% of the work in the Manhattan Project, more than 90% of the work. Both plutonium production and uranium enrichment are tricky, as Kate will describe. Number 2, making nuclear weapons that are really efficient, safe, that's a really hard problem, reliable, predictable, you can launch them on a missile. Unfortunately, to make a crude bomb that isn't any of those things, it's inefficient and unsafe, and you have to pack it in the back of a van and so on, and you have no real idea what the yield is going to be that a terrorist group might use is unfortunately way, way easier than making the nice kind of bomb that a state would want to have in its arsenal. And then really, really hard is designing and making a hydrogen bomb. No state has ever managed to do that without testing, and there's only a handful of states that have ever done that. There isn't any fundamental secret, but there's a lot of hard engineering and manufacturing stuff involved in making nuclear weapons.
Which are the states that have made hydrogen bombs?
United States, Russia were the first, China, France, Britain, claimed North Korea. There are both, well, India has made some assertions that I think are probably incorrect. There is widespread speculation that Israel might be in that category, although I doubt that they went for the full thermonuclear, just because it is very hard to actually do it without testing. There's a whole other area we can talk about in Q&A if you want, called boosting, which is a lot easier than full thermonuclear. If I were guessing, and I would only be guessing, is probably the direction Israel went.
Sorry, a hydrogen bomb is a subcategory of a thermonuclear bomb?
Well, they're same term.
Okay.
The two terms that mean the same thing.
And just on the North Korea claims, what are your thoughts on them about claiming to have tested a hydrogen bomb?
So they tested something that had quite a substantial yield. I would say the simplest explanation is that they're telling the truth. Because the thing they showed us a photograph of, which who knows whether that bears any relation to their actual nuclear weapons or not, but it looked kind of like a modern thermonuclear weapon, and the yield was suitable for a modern thermonuclear weapon. You can get that yield with pure fission weapons as well. Mm-hmm. There was an amazing U.S. nuclear weapon designer named Ted Taylor who designed the largest all-fission weapon ever tested, and also the smallest physically nuclear weapon ever tested, and is also one of the obscure facts about Ted Taylor is that he's, as far as we know, the only person who's ever lit a cigarette from a nuclear bomb blast by holding a parabolic reflector up to the blast and putting the cigarette in the focus. All right, a little bit about effects. So when a nuclear bomb goes off, you have this unbelievable release of energy that happens in like millionths of a second. And so the energy hasn't had time to go anywhere from this tiny little ball of nuclear material. And so if you think about it, that must mean that tiny little ball is at temperatures and pressures that are just unbelievable. And so it just explodes outward with an amazing amount of energy, and in particular radiation, which then creates this fireball. So this is the first ever such fireball in the Trinity test. So the shock front is where the incredibly pressurized air is rushing out in each direction, and it gets sort of magnified by reflection back from the ground, which is why that's called the Mach front there. And you can see the technical term of dirt cloud, because it sucks up a lot of dirt if you do it near the ground. So you have, what happens is the radiation goes out, it heats up this huge fireball. The fireball is an incredibly hot temperature. That hot air rises, so it begins to rise. It continues to expand. Wind comes in from around, because the air is going away, so there's low pressure. So you end up with the typical mushroom cloud that is sort of the symbol of fear of the nuclear age. So a bunch of the energy is released in the form of radiation. A bunch of it is released in the form of blast that knocks down buildings, and a bunch of it is released in the form of heat, which can set fires over huge distances and burn people over huge distances. So this is from an amazing tool that Alex Wellerstein created called NukeMap, which takes data from US government nuclear documents from testing and so on, and puts it with Google Maps so that you can drop a bomb on any city that you like, of any size that you like, at any altitude that you like, and it'll show you the effect. And secretly, more or less, Alex keeps track of who people bomb. So you can talk about that if he wants. A lot of people bomb their hometowns first, or the capital city of their country first. So this is a 10 kiloton bomb in Manhattan, and you can see that more or less all of Midtown Manhattan would be in the zone of pretty much lethal effects. Then this is the fallout. When the fireball is on or near the ground, so a surface burst as it's sometimes called, it sucks up a huge amount of dirt, rock, etc. And then that gets contaminated by the nuclear, what are called the fission products, the things you get when you split the atom, the products of fission, so fission products. And then it starts to rain down with all this radioactive stuff on it, and that's called fallout. And you can see in this particular example, the wind is such that you don't really have a problem over at West 42nd Street. But if the wind was just a little bit different, you'd basically have to evacuate all of Manhattan. And if you take that map out, there are people, 10, 20, 30, 40, 50 miles away who are probably going to have to evacuate. And so you can imagine the scale. And that's smaller than the Hiroshima bomb. That's sort of at the high end of what terrorists might conceivably be able to accomplish. Almost all nuclear bombs today are bigger than that.
So this would be a low-yield weapon, is what you're describing here?
Well,
So
not
just
as
small
low
weapon?
yield as you can go. So in the debate right now, one of the things the Trump administration is proposing is we do already have in the US nuclear arsenal some weapons that are called dial-a-yield weapons, where you can choose it to be quite a low yield or you can choose it to be quite a high yield. and they're proposing more of those, and in particular a submarine-launched one.
Can you
Yeah.
explain why you categorize bombs by this type of weight measurement? Because the actual material is much less, so why
Right.
do you?
So the weight measurement is the equivalent amount of high explosive that in terms of energy. So one of the things I have my students do each year is calculate how long a train carrying the explosives that would be the equivalent energy of the Hiroshima bomb would be. And an answer is it's 1.5 miles long train of explosives. That one bomb is the equivalent. So for relatively modest bombs, we use kilotons or thousands of tons of conventional explosives, and for substantial bombs, we use megatons or millions of tons of conventional explosives.
How does altitude affect the bomb?
So if you do an airburst, what happens is you don't suck up all that dirt and debris, so you don't have the fallout, but you have a great advantage because you're not using half of your energy digging up rocks and stuff like that, and you have sort of, you have the direct blast wave, but then you also have a reflected blast wave that amplify each other, and so you kill people over and destroy buildings over a much bigger distance if you're at what's called the optimum height of burst. And the optimum depends on how big your bomb is and also what you want to destroy. So you have to be closer in if you want to destroy something that's really protected. If you only want to, knock down brick buildings or wood buildings, then higher up is better.
Wait, run that by again?
What?
Say that one more time.
So if you want to destroy something that's really hardened, like a missile silo, you got to be either on the ground or pretty close to it. Whereas if you want to destroy, say, brick buildings, if you're attacking a city, then much higher in the air is suitable. So this, people often look at the overpressure, that is the shock, the amount of shock wave, as one of the key effects, and this is just to give you an idea. If so, normal atmospheric pressure is about 14 pounds per square inch. If you have enough shock that you're just more or less doubling the atmospheric pressure, 98% of the people in the zone where that's true will die. Here, only about half the people will die, but almost everybody's injured at 5 to 12 pounds per square inch. Here, not so many people die, a lot of people are injured, and out at 1 to 2, you've got a lot of injuries, but hardly any deaths. But you have a zone in the middle of almost total death. Now, my colleague Nick Roth and I, if you really want to depress yourself, have a recent article in the Bulletin of the Atomic Scientists that just describes what happens to a city if even a relatively modest nuclear bomb goes off in the heart of a city. And it's really, it's a horrifying little piece of, and of course, we don't have to speculate about that. There's human memory about that from the United States being the only country that has ever actually used nuclear weapons against defenseless human beings. I had the opportunity early last year, about a year ago now, to spend a day in Hiroshima with one of the last surviving hibakusha, and that was quite a moving experience. Hibakusha are the survivors of the Hiroshima and Nagasaki blast. So, just to remind you, there are roughly 15,000 nuclear weapons in the world today. This is who has them. More than 90% of them are either in the United States or Russia. Probably the North Korean number should be higher than it is on this chart. There's a sort of debate where 15 is sort of the low end and 60 or so is the high end, I would say, for current North Korean holdings. Pakistan and India have the world's fastest nuclear arms competition. Those numbers would have been less than 100 if I was doing this a decade ago. But the good news is, I mean, there are many pieces of good news we can talk about more in the Q&A, but there are 85% fewer nuclear weapons in the world today than there were 30 years ago. So we have actually made progress, and I can talk about a lot of other progress we've made, but I've gone on too long, and I should turn it over to my colleague, Kate Turner. who will tell you about plutonium and high energy uranium. And I'll be back here for Q&A.